Welcome to the 4.8 lesson video. We're going to make things a little bit more complex today when we talk about complex numbers. Our objectives are we can identify, graph, and perform operations with complex numbers, as well as we can find complex number solutions of quadratic equations. So let's begin by talking about what the complex number set is. The set of complex numbers includes imaginary and real numbers, as you can see in this diagram right here. We are used to working with real numbers, and today we're going to learn what imaginary numbers are. Every quadratic equation has solutions. Some of those solutions are real, which is what we've been doing up to this point, and some of them are imaginary, and this is what we will be learning today. A common misconception is that imaginary numbers don't actually exist. Well, to combat that common misconception, imaginary numbers actually do exist. And the reason why they're introduced is to be able to solve quadratic equations of the form x squared plus k equals 0, where k is a positive. The imaginary unit I is the complex number whose square is -1. The imaginary unit I is a number, not a variable, and it is defined as the square root of -1. So you can see right here, I equals square root of -1. And when you square both sides, you get I squared is equal to -1. Now let's focus on the key concept box on the bottom. So we have a general case for any positive number a. If we're taking the square root of -a, what we can do is factor out the -1, put it in front, and multiply by a, so that's still equivalent to the original expression. And then from there, break apart the radicals. So you have square root of -1 and square root of a. From there, we just learned that square root of -1 is equal to I, the imaginary unit I. So that means you can just replace the square root of -1 with I, and then square root of a cannot be reduced. So that would be the final form. Here's an example with a number involved. So we have square root of -5. So starting off with that, we're going to follow the same process that I just talked about. So you take the number 1 and you factor it out. So -1 times 5 underneath the radical. And then you take the square root of -1 times the square root of 5. And then square root of -1 is equal to I. And square root of 5 just drops because it's not a perfect square. So that would be the simplified form of the original expression square root of -5. Hopefully you remember from working with radicals in the past that when you square a radical, the exponent 2 and the radical actually cancel out because they are inverses of each other. Just like when you add and subtract things, those cancel out. So you just end up with a number underneath. So this note at the bottom is just saying when you square root of -5, you just get -5, which is the number underneath the radical. In example 1, we need to figure out how to write square root of -18 by using the imaginary unit I. So first of all, we know that square root of -18 is not a real number because there is no real number that when multiplying by itself, it gives you -18. So that means we must use the imaginary unit I to write the square root of -18. So first step I'm going to do is rewrite the given, and then from there I'm going to factor out the -1. So I have, under the radical, I have -1 times 18. From there, I can break apart the radical, so I have square root of -1 times square root of 18. The first part, the square root of -1, is just equal to I. And then the square root of 18 can actually be split up into square root of 9 times square root of 2. Hopefully you agree that when you're reducing radicals, you want to see if there's a perfect square factor of it, and the biggest perfect square factor of 18 is 9. In this case, 9 is the only perfect square factor of 18 besides 1. But in other situations, when you're dealing with numbers under the radical, you want to pick the biggest perfect square factor to make your simplifying process easier. So from there, we know that square root of 9 is equal to 3. So I'm bringing down the imaginary unit, and then 3 square root of 2. And then lastly, we want to multiply, and typically put a regular number, a real number, in front of the imaginary number. So 3i times the square root of 2. That would be square root of -18 using the imaginary unit I. Let's talk about what an imaginary number is. An imaginary number is any number of the form a plus bi, where a and b are real numbers and b is not equal to 0. As I mentioned in the beginning of the video, the imaginary numbers and the real numbers together make up the set of complex numbers. Take a look at the key concept box. Right here in the middle we have a plus bi. The a is the real part and the b is the imaginary part, and together they form a complex number. So here's an example. 2. The number 2 is a real number because essentially we have 2 plus 0i, and the 0 cancels out the I. So 2 is a real number, and that's the kinds of numbers that we're used to working with so far. Imaginary numbers. Here's an example of an imaginary number, 2 plus 2i, because the b, the number in front of the I, is not equal to 0, so that means there is an imaginary part to it. And then a pure imaginary number would be an imaginary number where the real number is actually 0, so the only piece left is the imaginary part itself, and an example of this would be 2i. In general, we cannot order complex numbers since they cannot be graphed on a real number line. However, using a complex number plane, we can graph the complex number a plus bi, where ab is a point on that plane. So to graph a complex number, we want to locate the real part on the horizontal axis and the imaginary part on the vertical axis. So you can see in this graph at right, we have the real part on the x-axis or the horizontal axis, and we have the imaginary part on the imaginary axis or the y-axis. To graph the complex number 3 minus 2i, we start at the origin and we go 3 units to the right because it's a positive 3. That's on the real axis, and then down 2 because it's a negative 2i, and that's the imaginary part. We can find the absolute value of a complex number by finding the distance from the origin in the complex plane. So we just graphed the imaginary number 3 minus 2i. We can find out the absolute value of 3 minus 2i by finding the distance away from 0. And hopefully you remember that the distance away from 0 is the absolute value. So instead of just taking the absolute value of one of the two terms, we're taking the absolute value of the sum of the a and the b. So take a look at the bottom right here. I rewrote the expression, the absolute value of 3 minus 2i. The a is the 3 and the b is the negative 2. So from there we just need to square the 3, so 3 squared, and then square the negative 2, so negative 2 squared. And when we add those together we have 9 plus 4 and the square root of 13 simplified. So that would be the absolute value of the complex number 3 minus 2i. In example 2, we are given two different complex numbers and we need to graph them as well as find the absolute value of each of them. So let's start off with part A. We have negative 5 plus 3i. Make sure when you're making your graph that you label the real axis as the horizontal axis and the imaginary axis as the vertical axis. So from there you're starting at the origin. The a is negative 5, so that means for the real number we're going 5 to the left. So count over 5. 1, 2, 3, 4, 5. And then it's going to be 3 up since the imaginary part is positive 3i. So this will be the location of the complex number negative 5 plus 3i. Now let's graph 6i. You may have noticed that there is no real part to this, so essentially we have 0 in front, so 0 plus 6i. That means we do not have to go left or right at all. And since it's a positive 6i, that means we're going to be counting 6 units up from the origin. So this would be the location of the number 6i. When finding the absolute value of the complex number negative 5 plus 3i, I'm going to label a and b. Remember, we just did this on the previous page. You just need to square each of the a and the b terms and then add them together. So we're squaring negative 5, we're squaring 3, and we're adding them together. So when we do that, we get square root of 34. So that would be the distance from the origin. When finding the absolute value of 6i, I'm breaking it apart and I'm writing 0 plus 6i. The a is 0 and the b is 6. So when I square 0 and square 6 and add those two numbers together, I just get square root of 36, which is equal to 6. That should make sense to you because we can visually see that 6i is 6 units away from the origin. I'm about to teach you how to add, subtract, multiply, and divide complex numbers. When you're adding or subtracting complex numbers, you want to combine the real parts and the imaginary parts separately. This is very similar to adding algebraic expressions because adding the real parts and the imaginary parts separately is just like adding like terms. So that means in example 3, part A, we're just going to be adding the 4 and the negative 4 together. And then separately, we're going to add the negative 3i and the positive 3i together. So the real numbers combine and the imaginary numbers combine separately, so like terms. So to make part A easier, I just reordered the problem, and we're just using the commutative and the associative properties to do that. So now I have my real numbers next to each other, 4 and negative 4. When I combine those, I just get 0. And then I have my imaginary parts next to each other, negative 3i and positive 3i. When you combine that by adding, you also get 0. And when you add those together, you just get 0. So that means the sum of these two complex numbers is 0. And the reason why the sum is 0 is because these two expressions that we started with are called additive inverses. For part B, we're given 5 minus 3i minus the quantity negative 2 plus 4i. So first thing, before sorting like terms, I want to distribute that negative 1 in front of that second set of parentheses. And remember, when you multiply by negative 1, you're only changing the signs. So the first expression is the same. So I have 5 minus 3i, and then now I have plus 2 minus 4i. Now I want to sort the like terms, so I'm going to have 5 plus 2 minus 3i minus 4i. So just make sure that the signs in front are staying with the numbers. From there, I just need to combine the 5 and the 2, so 5 plus 2 is 7, and then combine the imaginary numbers, and that would be minus 7i. So the simplified version of the original expression is 7 minus 7i. Now that we just did an addition and subtraction problem, we're ready to learn how to multiply complex numbers. The good news is when you multiply complex numbers, it's the same kind of process as when you multiply binomials. So hopefully you remember the distributive property, FOIL, and table. Those are the methods that help us multiply binomials, and those are the same methods we can use to multiply complex numbers. So let's begin with part A of example 4. We're given 3i times the quantity negative 5 plus 2i. I'm going to distribute the 3i to both terms inside the parentheses, and I'm going to get negative 15i plus 6i squared. Remember that I squared is equal to negative 1, so negative 15i drops, but then for the I squared, I'm going to multiply by negative 1. So that means I have negative 6 as the real part of the answer. So we always write the real part first. So negative 6 minus 15i is the product of the original expression. So remember, the answer is always in the form a plus bi, where the a is the real part and the bi is the imaginary part. Now in part B, we're given the product of two binomials. So in part B, I'm going to use the FOIL process. Remember, first, outer, inner, last. That's what FOIL stands for. Okay, so I'm going to multiply the first two terms. 4 times negative 1 is negative 4. The outer terms multiplied is negative 8i. The inner terms multiplied is negative 3i. And the last two terms multiplied is negative 6i squared. From there, I want to combine like terms. So I still have negative 4. The middle two terms are like terms because they just have a regular I after them, so that means we get negative 11i. And the last term has an I squared with it, so that means we're going to do the same thing as part A. We're going to substitute negative 1 in for I squared. And when we multiply negative 6 and negative 1, we get positive 6. So I'm just going to put the positive 6 next to the negative 4. And you're probably guessing that we're about to combine those real numbers, and you are right. So negative 4 plus 6 is equal to 2, and then drop down the 11 minus 11i. So that means 2 minus 11i is the product of the binomials that we started with. For part C, when multiplying these two complex numbers, we could use the FOIL process again. To cover all the bases, I'm going to review the table method with you. And when I teach this to my freshmen when teaching them how to multiply regular binomials. A lot of them prefer this because it is very visual. So make yourself a 2 by 2 table. The reason why is because both of the expressions or the complex numbers have two terms involved, a real part and an imaginary part. And then from there, I typically use the first set of parentheses as the side, so label -6 and I. And then on the top, I'm taking the next set of parentheses, so -6 and -I. And then to get the pieces inside the table, you just need to multiply, just like in the FOIL process. So -6 times -6 is positive 36. -6 times -I is positive 6I. -6 times positive I is -6I. And I times -I is -I squared. So just like in the FOIL process, there are combining like terms, and we have the like terms on the diagonal. 6i plus a -6i is just 0i. So essentially we just have 0 there. So that means our answer is going to be found from simplifying 36 minus I squared. And remember, I squared is equal to -1, so that means we have 36 minus a -1, which is a double negative, so that means we have 36 plus 1, which is equal to 37. So believe it or not, from the complex numbers that we started with, we're getting a nice answer of 37. So in part C, we started off with two complex numbers, and when we multiplied them, we got a real number. This concept is called complex conjugates. So when you have number pairs of the form a plus bi and a minus bi, the imaginary part will cancel out and you will get a real number for your answer. So like I said, complex conjugates are of the form a plus bi and a minus bi. When you multiply these complex conjugates, or the product of these two, it's a real number. We can use complex conjugates to simplify quotients of complex numbers, and that's what we're about to do in example 5. In example 5, we need to figure out the quotient of each of the complex numbers by dividing. So what we want to do is multiply the numerator and denominator by the complex conjugate of the denominator. The goal is to have no imaginary unit I in the denominator in your final answer. In part A, we are given the complex number 9 plus 12i over 3i. So what we want to do is multiply that complex number by the conjugate of the denominator. The conjugate of 3i is -3i because they are opposite signs. When we multiply by -3i over -3i, we're essentially just multiplying by 1. So that's okay. We're just changing the form. We're not changing the actual value. So when we do that, we're going to distribute the -3i to both terms and the top. When we do that, we get -27i minus 36i squared. In the bottom, we get -9i squared. From there, we can substitute -1 wherever we see I squared. So I'm going to keep the -27i and then minus 36 times -1. And in the bottom, we have -9 times -1. So you can see that the i's are going away. So now we have 36, so I'm going to be putting the real part first, positive 36 minus 27i on top and positive 9 on bottom. And from there, we can divide the 36 by 9 as well as the -27 by 9. So we get a simplified form of 4 minus 3i. And that would be the quotient. In part B, we have 2 plus 3i over 1 minus 4i. So what we want to do here is multiply by the complex conjugate of the denominator. Since we have 1 minus 4i in the denominator, the complex conjugate is going to be 1 plus 4i. So multiply the top and the bottom by 1 plus 4i. Now we're going to be using the FOIL method on top and bottom. So when we multiply the top, we get 2 plus 8i plus 3i plus 12i squared. So I use the FOIL process for that. Now I'm going to do the FOIL process on the bottom. So I get 1 plus 4i minus 4i minus 16i squared. And you can see in the bottom, the positive 4i and the negative 4i cancel out. So that means that imaginary part is gone, which is the goal. So now I'm going to simplify on the top. So now I have 2 plus 11i plus 12 times -1 because we're substituting in -1 whenever we see I squared. And the bottom we have 1 minus 16 times -1. So on the top I have 12 times -1, which is -12, and 2 minus 12 is -10. And then the plus 11i drops. On the bottom, I have 1 minus 16 times -1. Well, -16 times -1 is positive 16, and 1 plus 16 is 17. And then lastly, we just need to share the 17 with both pieces, so that means we have -10 over 17 plus 11 over 17i. And that is the quotient of the original expression. In example 6, we're going to factor 2x squared plus 32. Before you do anything else, check to see if there's a GCF. I see that both numbers are even, so that means that they at least have a common factor of 2, and there's nothing else that's in common, so that means the GCF is 2. So I'm going to take 2 and put it in front. As always, the GCF is in front. Factor it out, and that means I have x squared plus 16 inside. This quadratic is of the form x squared plus k, where k is a positive. K is greater than 0. And if you can recall from the beginning of the video, we will need to be using imaginary numbers to factor this expression. We're not able to use real numbers when factoring this. Before we get to the factoring process, and it will be quick, I do want to help you recall how to factor the difference of two perfect squares. So I really just changed the x squared plus 16 to an x squared minus 16. We can do this by taking the square root of the front and the back. So this factored form would be x plus 4 times x minus 4. So hopefully you remember that from a previous lesson 4 video. So this is going to be a very similar process. The only difference is that we're going to have to tack on the imaginary unit I after each expression. So we still have 2 in front, but now we have x plus 4i times x minus 4i. So in general, if you want to factor a squared plus b squared, you just multiply a plus bi times a minus bi. You could always check your final answer in this situation by multiplying out your factored form. You may be wondering, why are complex numbers involved with quadratics? And that's this whole chapter. We're learning about quadratics. Well, every quadratic equation has complex number solutions that are sometimes real numbers. Up until this point, we've been only working with real number solutions. Now we're going to introduce the possibility of having imaginary solutions. So I'm going to show you that process in example 7. Bear with me, we're almost done. We're given the quadratic 2x squared minus 3x plus 5 equals 0. We want to use the quadratic formula to find the solutions. Like always, we always identify our a, b, and c values first. So we know that a is 2, b is -3, and c is 5. From there, we're going to be using the quadratic formula. Hopefully you remember this from the previous lesson video. It is x equals -b plus or minus the square root of b squared minus 4ac all over 2a. From there, I'm going to substitute in the a, b, c values. So I have minus a -3 plus or minus the square root of -3 squared, make sure you use parentheses, minus 4 times 2 times 5, all over 2 times 2. Now let's simplify that and figure out what our solutions are. So we have positive 3 in front, and then when you combine everything under the radical, you get 9 minus 40, which is -31. So we have square root of -31 all over 4. Well, we learned how to work with square root of a negative earlier in this lesson, so we can rewrite that as I times the square root of 31, and that work is shown in the bottom left corner if you need to see it. So now we just need to share the 4 on the bottom with both pieces. So that means we get 3/4 plus or minus square root of 31 over 4 times the imaginary unit I. So that would be our 2 solutions from there. Thank you so much for sticking with me. If you are listening right now, put a little smiley next to example 7. I very much appreciate you listening and keeping up with me. Yes, this was a very long video, but I'm hoping that it was very beneficial to you. Here are our lesson check problems for this lesson. Please write them down, work through them, and let me know if you have any questions tomorrow when we meet.